In this video, we're going to talk about linear combinations. So to begin with a definition, let U and V be vectors in a vector space, capital V. Let A and B be scalars. The expression A times U plus B times V, and let's highlight that, is called a linear combination of vectors U and V. All right, so let's look at a few examples. So first example, let U be the vector given by 1, 2. And again, lots of ways of expressing that vector depending on your book or depending on the context. I'm going to write that vector in 3 different ways, including as a column vector. So we've got vector U equals a vector 1, 2. And let's also consider a vector V given by the vector 3, 4. And again, lots of ways of writing that vector. And so we've got some vectors. The directions say write a linear combination. Write a linear combination of U and V. Of U, vector U and V, using any scalars you like. Using any scalars, we'll say A and B are elements of the real numbers. So any real scalars. So lots of correct answers here. I'm in the mood for a 3, so I'm going to say 3U plus negative 5. That's a perfectly fine choice of a scalar. Negative 5 times V. So we've taken real numbers times a vector, another real number times a vector. That is a linear combination. So this is a linear combination. This is a linear combination. It's a way of combining the U and the V in some sort of linear fashion, linear combination of vectors U and V. Now we could certainly work this out a little bit more, so let's do that. 3 times U would be 3 times our vector 1, 2. And we've got a negative 5 times a vector V, which is 3, 4. So we could work this out. If we work this out a little bit, we get a 3, 6 for the first vector, and for the next vector we get a negative 15, negative 20, and now we can do vector addition, add those up, and we get a negative 12 and a negative 14. Okay, here's a different problem, different type of problem. So in this problem, different example, so let's determine if vector W, so here's vector W is given by 8, 0, 5. Determine if vector W can be written as a linear combination of vectors U, so U will be the vector 1, 2, 3. We got another vector here, vector V. So we'll take vector V. Vector V is given by 0, 1, 4. And vector T, so let's get a different color here. We'll get our green color here. Vector T, 2, negative 1, 1. All right, so here's our task. Our task is to determine scalars A, B, and C. And again, these are going to be real numbers. So A, B, C, and the elements of the real numbers. Our task is to determine scalars A, B, and C such that vector W equals some scalar A times vector U plus scalar b times vector v plus c times vector t, if such scalars exist. Right, so if they exist, we can certainly write w as a linear combination of the other vectors, and if the scalars don't exist, then we can't do it, and we'll just say that. All right, so how would this work? If we want to satisfy this equation here, what we need to do is we need to write w. Now w is the vector 8, 0, 5, and supposedly that equals a times vector u. Recall that vector u is the 1, 1, 2, 3, plus scalar b times vector v, which is a 0, 1, 4, plus c times vector t, which was a 2, negative 1, 1. All right, and so we need to see if these scalars a, b, and c exist. So we need to solve for a, b, and c. Okay, and I've taken the liberty of writing down the next line in our calculation. So if we perform scalar multiplication, we get 1a, 2a, and 3a, and so forth for the remaining two vectors. And now what we want to do is we want to add up these vectors, so we can do vector addition. On the left-hand side, nothing's changed, so I'll copy that over. And then on our right-hand side, we're going to get a big vector here, and we're going to have a 1a plus a 0b plus a 2c. And that's our first component. In the second component, we're going to get a 2a plus a 1b minus a 1c, or plus a negative 1c. And then in the third component, we'll get a 3a plus a 4b plus a 1c. Now we're in a good position to start equating the different components here. So this 8, this is in our first component. And over here on the right-hand side, we have a very big expression. Oh, I overdid it a bit there. A very big expression here for the first component on the right-hand side. And so if we equate those first components, the first component's equated, so that gives us our first equation, and then our second components, which are 0, equals 2a plus 1b plus a negative 1c, and then our third components here give us the third equation. Once we have three equations, three linear equations and three unknowns, we can write this as an augmented matrix. And so our coefficient matrix here, if we read down the coefficients for the A's, we get 1, 2, and 3. Second column for the B coefficients, we get 0, 1, and 4. And for our coefficients on the C's, we get a 2, negative 1, 1. And then we have a column of constants here. Our constants were 8, 0, 5. Okay. We can use Gauss-Jordan elimination to RREF this, or we could put it in MATLAB. So once we have that matrix, we RREF it, we get down to the final solution, and so we discover our scalars A, B, and C. And what this means is that we can have 2, oops, let me choose a different color for that, 2 times vector u plus a negative 1 times vector v plus a 3 times vector t, that equals w. And so to answer our question, can w be written as a linear combination of u, v, and t? Yes, it can, so let's just say that. So vector w can be written as a linear combination of vectors u, v, and t. So u, v, and t. Great.